Thank you very much. It's great to be here. Thanks for inviting me, and I'm sorry I'm not there in person. So this is joint work with my colleague John Ergen and Doric Chedeman. I have to apologize in advance. While we have in this paper individuals whose choices aggregate into stuff that affects everyone in the group, we are not taking an axiomatic approach, and we will do the unspeakable, which is using interpersonal comparisons of utilities. So if it makes you shudder, feel free to extend your coffee break, and I apologize. All right, so our motivation for this project is the observation that many collaborative activities involve search. So if you think about policy design or research and development, joint ventures, startups, and so on and so forth, in a lot of cases, we have a team that develops something. So just to give you a concrete example, for instance, in 1993, the Partnerships for a New Generation of Vehicles was formed, and it involves various federal agencies and universities and a bunch of car manufacturers like Chrysler, Ford, and GM. And they were really doing research and development together in collaboration, but ultimately each entity dropped off this enterprise and went on to develop its own thing. So be it research or car models and so on. So these are kind of the features that we're trying to get. The fact that in research and development, often these observations build upon one another. So there's some inherent correlation in what people look at. When you're participating in a team, each individual or entity needs to decide how ambitiously to search. And ultimately, when search terminates, people implement whatever is the best option they've seen up to their termination. All right, so in this model, the main components are going to be the following. So we're going to have uncertainty and correlation that's governed by a Brownian path. So this kind of captures this idea that ideas or prospects are correlated over time. And whenever agents stop, they implement the best idea they've seen up to now. The search scope, which I'll soon be more formal about, is jointly controlled. And the way we think about it is as the variance of the Brownian path. So that's what individuals are selecting. And a higher variance comes at a higher cost. So that's kind of a breadth of search. Our goal here is to understand how search unfolds over time in these collective settings. Okay, so just to foreshadow what I'll tell you, in terms of how the search scope or ambition or search breadth vary as a function of search outcomes, what I'll try to show you is that the search scope is actually constant and depends only on the set of active agents. So it doesn't depend on the observations you've seen so far, or the maximal observation you've seen, etc. In terms of exit decision, when do people actually stop search in this collective process? We'll see that there's a deterministic exit sequence, which occurs at random times. And there's a simple stopping boundary that actually governs these exit waves that we'll see. So by exit wave, what I mean is that once one agent terminates her search, a bunch of others will follow suit immediately. And in terms of efficiency, there are externalities all over the place here, so you won't be shocked to hear that equilibrium is inefficient, but we can actually identify what form the inefficiencies take. And if I have time, I'll show you that the social planner would like agents to search longer with higher scopes and might implement a different sequence of exit waves, which is perhaps more interesting. The first bullet point is more an artifact of externalities directly. All right, so I won't, given the length of this talk, I won't give you an exhaustive lit review, but let me just mention kind of broad areas that this connects to. So first of all, this idea of searching on a Brownian path, Steve Callender deserves a whole lot of credit for this. This was his kind of innovation. And there are a bunch of papers that followed suit. importantly, from a technical perspective, these earlier papers could only solve very short-lived agents, so effectively myopic agents who optimize myopically. And we're going to have long-lived agents. We also have a breadth of search that we can analyze, and we put it all in a collective setting. Another really important contrast is that with experimentation. So some of you may be familiar with the canonical work by Bolton and Harris and Keller, Ruddy, and Cripps. And the idea there is that a group actually experiments to find a good option. Now, what's the difference? Let me find here my exhibit. So suppose that in experimentation, I'm trying to figure out whether this coffee is good. So what I do is take little sips, and every sip is informative to me, and ultimately I can decide whether the coffee is good or bad. And in our search setting, what I'm trying to do is actually develop a new coffee. So I start with some coffee, maybe I add a little bit of cardamom, maybe I add a little bit of sugar, and so on and so forth to develop a new brand of coffee. And there is a bunch of work on optimal stopping. I'll just wave these names at you, and I hope that's okay. All right, so here's what I'll do to you in the next 30 minutes or so. So I'll start with the model. Then I hope to be able to describe to you fully the equilibrium. And if I have a couple of minutes, I'll tell you something about the social planners problem, just so we understand where the inefficiencies emerge here in this collective setting, and then we'll be done. All right, so here's the model. So in our setting, time is continuous and indexed by t, that's time. There are n agents who decide when to stop searching. And when you stop search, that's an irreversible decision. Now, A sub t is going to denote the alliance of agents who are still active at time t. So this is going to capture really the inherent dynamics of this process. At any point in time, there is a certain set who is still searching. A sub 0, just for convenience, it's going to be the full set of agents. Now, active agents jointly control the search. So what I mean by that is that the search itself, the outcomes of the search X, follow a Brownian motion with a variance that's the sum of these individual search scopes, which the next slide will detail. And we'll just assume that the starting point is 0. All right, so what about this variance? So agents each choose an individual search scope. This is this breadth of search. And we assume that it's taken from a compact set where the lower bound is strictly bigger than 0. So what this rolls out is just situations where people are idling, not doing anything, and just observing other people working and reaping the benefits. So we want to rule that out. The cost is strictly positive and satisfies kind of standard assumptions. So it's increasing, it's convex, and it's continuously differentiable for everyone. And I'll note that while most of the literature on these collective decisions assumes homogeneous agents, for us here, the homogeneous agent case will be actually the less interesting case. What we'll be really interested in is when we have fully heterogeneous agents. In some sense, then the fact that we have these exit waves will be more interesting, perhaps. And agents perfectly observe other agents' choices. So we're not dealing here with some sort of imperfect monitoring information, etc. Okay, it will be really important to have the maximum process down. So when you stop, you collect the best thing you've seen so far. And the best thing you've seen so far corresponds to the maximal observation. So that's going to be this M sub t, which is just the maximal observation of the search up to time t. And since we assume that the process starts from 0, we'll also assume that the maximum starts from 0. So at time 0, M0 equals to 0. Now, just to understand kind of this meaning of the search scope, for any fixed search scope, sigma, at any time t, if you looked at the expectation of the maximum, it would be proportional to sigma, or the search scope. So in other words, the search scope translates directly into returns from search. Now, agents decide when to stop, And when they stop at time tau, they get the maximum accomplished up to time tau. Everyone else continues searching and may get a higher maximum when they stop. In principle, you could also think about adding penalties for later exits, which might have some empirical relevance. Perhaps you kind of capture a market segment if you exit early. This would mechanically lead to people exiting at the same time if you get punished for exiting a bit later. But the qualitative analysis remains kind of similar to what we're doing. So I won't say much more about this today. Okay, so the agent I's total payoff when she stops at time tau is just the maximum at time tau minus the flow cost that she exerted while searching. A strategy for agent I then has two components: the search scope at any time. So at any point in time, she needs to decide how broadly to search, and the stopping decision when she stops searching. And we'll restrict attention to Markov strategies that depend only on the observed level of search, that's X sub t, the maximum observed up to now, M sub t, and the alliance, the people who are searching with you. All right, now, just because this maximum is really important, let me just show you a graph, and I'll soon show you another graph that's related to it. So we have it down. So what you see here in the black graph is just a sample path of X sub t. What you see in the green line is the corresponding maximum. So whenever there's an increase in the path, the maximum increase. Whenever you don't have an increase in the path, the maximum process remains flat because the maximum observed up to this time did not change. Now, when you look at this segment, for example, here it looks as if the green and the black coincide. That's actually a bit of an optical illusion because the measure of times at which this happens, where the maximum coincides with the search value, is of measure 0. All right, now we're gonna assume a stopping boundary that is continuous. So stopping boundary just tells you when you want to stop. Intuitively, because we have correlation here, when results are sufficiently bad, you're going to stop. You're going to give up because it's going to be prohibitively costly to exceed the maximum you've already achieved. So we're going to have this function that governs the stopping boundary that we denote by GI of A. It depends on the active people right now, the alliance that's searching A. Now, the assumption that this is continuous might seem weird because this is an endogenous thing, but as it turns out, this is without loss of generality if each agent is willing to search on their own. So then we have a family of stopping times that depend on the alliance that's active at the moment. All right, so just to give you an example of what this means practically. So this is an example of two different stopping boundaries, and they're the silliest stopping boundaries you could think of. They're just the 45-degree line shifted by a constant. So here, the red line corresponds to m-2. So this means that if the observation you see is below the maximum you've collected by at least 2, you stop. And here, if the distance between the current observation and the maximum is at least 3, you stop. And what you see on the right-hand side is just a figure that I showed you before, but with the corresponding boundaries superimposed. And unsurprisingly, what you see is that the red line is always above the blue line. You can already see it on the left here. And in fact, the other thing to note here is that a smaller distance corresponds to a more demanding person. So the smaller the distance, the quicker you will be to stop. So here, the red person is always going to stop before the blue person. Here, they're stopping over here. All right, so now we're ready to characterize the equilibrium. So again, how do we think about equilibrium here? So each agent chooses their search scope, sigma j, and their stopping time, tau sub j. And then the agent's problem is just to maximize their objective given what everyone else is doing. So this is pretty standard. So this is just to remind you, this is their objective is just the maximum they get when they stop minus the flow costs that they exerted while searching. An equilibrium is a profile of Markov strategies, that's a restriction, constituting best responses for all agents. Now, Markov makes our lives much easier. I will note, however, that some of the inefficiencies that we highlight do not vanish if you assume non-Markovian strategies. All right, so let's start with the search scope. So for any agent I in an active alliance A, equilibrium search scopes are constant. So in other words, the search scope depends only on the active members of the alliance that are still searching, but not on the features of the path up to now. And whenever they're interior, they're identified by this system of equality. So interestingly, you'll see that the cost over the marginal cost play a really important role here. So equilibrium search scope depends on A sub t. So I'm sorry for repeating myself, but not on X sub t or M sub t. And if you have log convex cost, this just translates into monotonicity of the left-hand side here, and then we know we have a unique solution. So that's pretty convenient for us. Now, it's really important that we have this ratio of C to C prime here, because it means that sometimes a higher cost and a higher marginal cost, both together, as long as the ratio behaves in the right way, are actually quite desirable. Now, if costs are log convex, when we have uniqueness, we can do nice comparisons. As alliances shrinks, individual member search scopes increase. And this is just a manifestation of a sort of free riding. So when I'm working with a lot of people, I can free ride on them. As people drop off, I have less free riding opportunities, and therefore I exert more effort. So that's basically what this corollary tells us. All right, let me give you a rough intuition for where this is coming from. Why do we have a constant search scope? So for each agent I, given the strategy of everyone else, this is basically what they're optimizing. They're just, again, this is their objective given what everyone else is doing. Now, if you think about a point at which you're far away from the maximum, infinitesimal changes in your search scope are not going to affect the maximum itself. You're far away from the maximum. Tiny changes right now are not going to affect it. Now, you might say, well, what about times at which the maximum exactly coincides with the search values? Well, recall that I told you that this happens with a measure 0 of times. So this very rarely happens. So what this tells us is that effectively, we don't really need to think about the effect of the search scope on the maximum. What we really need to think about are these flow costs. Now, when you look at it at face value, like immediately, you might say, well, then I should just minimize my search scope to minimize the cost. Well, the problem is that we have some trade-off because you're also affecting the time at which you'll get to the stopping boundary. So we need to trade these off, kind of the speed and the time it will take you to get there. So each agent is going to minimize the expected cost locally. And now how do we do this? So how do we break this trade-off? So as it turns out, the search scope sigma is equivalent to speeding up time by a factor of sigma squared. So that's a nice feature of Wiener processes. So keeping the path fixed, changing sigma is just like changing the speed at which you traverse the path. So expecting time is inversely proportional to this overall search scope squared. That's just the variance of the overall search scope in the team. So each agent ultimately finds an efficient speed. An efficient speed just means that the cost per unit of speeds are minimized. And if you look at the first order condition of this objective, then you get exactly what we have in the proposition. Okay, So now let's go to the stopping boundary. So proposition 2 tells us that there exists an equilibrium such that for any agent I and any active alliance A, the stopping boundary looks just like these red and blue stopping boundaries I showed you in the figure. So just like a 45-degree line that's shifted by a constant. That constant depends on the overall search scope in the alliance and the individual cost of search in this alliance. But ultimately, it's a very simple stopping boundary. So in particular, the person in the alliance with the minimal such constant, just like our red graph as opposed to our blue graph for the stopping boundaries before, is the first to stop in any alliance. Now, here I'm saying there exists an equilibrium. As it turns out, it's actually generates a unique equilibrium outcome if we impose some mild version of weak dominance. So if we're thinking about a situation where everyone knows the search scopes implemented in equilibrium and we're looking for weakly undominated strategies, that's the unique outcome that will emerge will be the one corresponding to these stopping boundaries. Okay, now these stopping boundaries, these shifts of the 45-degree line have a name in applied math. They're often called drawdown stopping boundaries, where the drawdown size, this is kind of how much you draw down from the maximum, is this constant. So for us, this constant is this d sub I superscript a. So each individual in an active alliance has this drawdown size. Now, again, lower drawdowns mean higher stopping boundary and therefore more demanding choices for continuation of the search. So the lower the drawdown, the quicker you stop. Let me give you a rough intuition for where this is coming from. So suppose we have an alternative problem where we just shift everything up by a constant. So we add the constant k to our search process. So this means that the maximum process is shifted up by k. And because we have here a linear utility and the maximum, we must have the same solution. It's essentially the same problem. And this immediately tells us that we're facing here a drawdown type of stopping boundary. Now I'm really cheating you here by showing this in such a simple way. We have here a game, so this is certainly not a proof, but hopefully it gives you kind of a feeling of why we should expect this. All right, so how do we get to exit wave? So in an alliance A, let's assume that DIA is the smallest drawdown size. So I just told you that smaller drawdowns means more demanding stopping. So the smallest, the person with the smallest drawdown size is the person who stops first. So let's assume that we just hit that person's boundary. So X sub T is exactly the stopping boundary of person I. So agent I is going to exit. And let's denote by Z0 the set that contains I. So the remaining agents, now they know that I has left and they need to contemplate a world in which they're searching without person I. That immediately makes them adjust their drawdown sizes because the drawdown sizes depend on a group of people searching. So maybe I search with Salvador, Salvador leaves, the world looks horrible, and I'm suddenly much more demanding to continue search. So now we have a bunch of people who will decide to leave immediately. So let denote by Z sub 1 these agents together with agent I. So now we can, so these people are going to exit immediately. So now we can consider the remaining agents. And again, they need to contemplate the world without all the agents Z sub 1 that are leaving and decide whether they want to continue or not. And we can continue this process until it stabilizes. So this will potentially generate an exit wave, the snowballing effect. So what this line of argument suggests is that the order of exits is deterministic. There's nothing stochastic here. All that we're using are these drawdown sizes where we have a formula for them. So who leaves first is going to be completely governed by these drawdown sizes. Naturally, their precise timing is stochastic because that depends on when the process actually hits the stopping boundary. All right, so I'd like to give you some sense of how these things look. So in order to do that, I'll put a little bit more structure on the problem. So let's assume that agents' cost functions are proportional. So this means that just agent one's cost is just a multiplication of agent two, etc. And we'll assume that these multipliers, beta 1 through beta n, are nicely ordered just without loss of generality. So what this means is that agent 1 is the most expensive agent, then agent 2, then agent 3, etc. Now, this is a good point to actually highlight what happens if costs are identical. So if costs are identical, everyone uses the same search scope and they all exit together. But this is not terribly surprising because if they're all the same, then naturally they're going to exit together. That seems very intuitive. So what will be interesting for us is if we see these clustered exits, even when we have full heterogeneity of costs. So in this case, agents, as it turns out from our proposition 1, choose identical search scopes. So recall that the search scope depended only on the ratio of cost to marginal cost. So these multipliers make no difference whatsoever for this ratio. So who will exit first? Well, naturally, it's going to be the person with the highest cost. So we have kind of a weak ordering of who will exit first. It's the most expensive agent, then the less expensive agent, etc. But it still doesn't tell us exactly who will exit first, then who will exit and who will cluster with them. So let me show you how that works in a figure. So here's the drawdown size that corresponds to person 1. Now we know that she exits first. So this is going to be the drawdown size that governs her first exit. But once she exits, we know that person 2 is going to be the person to potentially follow. Person 2 will need to contemplate a world in which she's searching with agents 3 to 10, with 1 gone away. Now, if her drawdown in that world is actually lower than the drawdown size of person 1 to begin with, she'll exit immediately. That was just our construction. Similarly, person 3. So here, we're ultimately, what we're looking at is all these drawdown sizes where you contemplate the world with the people who you know have left, and you ask yourself, do I want to leave as well or not? And what we see here is that person 1, 2, and 3 will stop first, then person 4 and 5, then 6, etc. Namely, what we're seeing here is that the upper envelope of this graph governs fully the set of exit waves. All right, so just to summarize the properties of equilibrium, search scope depends only on the current active alliance A sub t. It doesn't depend on the features of the search up to now. They're endogenous exit waves with deterministic order, but stochastic timing. And we have both a free riding and encouragement effect in the sense that as alliances shrink, each member chooses a higher search scope, that's free riding, and agents search longer in a team compared to searching on their own. So this is an encouragement effect. If I'm working with, say, Arunava, and I know he works really hard, that encourages me to continue on because he's there. All right, so in the last few minutes that I have left, I'd like to give you kind of a hint of what happens with the social planner. So the social planner solves a Markov decision problem, maximizing overall utilitarian efficiency. And this is where social choice theorists might shudder. Now, there's a lot of notation late in the day, so you can ignore the notation. Let me just say it in words. The social planners effectively controls what you probably imagined they would control. They can determine who should drop from any alliance at any point. And they can determine what is the search scope for each agent, even conditioning on the alliance at which they're searching. So at any time, they can decide who is terminated and what is the effort they put into this process. So the social planner's problem is ultimately to maximize the same sort of objective where they're just looking at utilitarian welfare. All right, so I'll just kind of wave at you the results to give you a sense of how things look here. So as it turns out, the social planner solution resembles the equilibrium in terms of structure. So the first proposition tells us that there's going to be a constant search scope within any alliance, and optimally. And whenever it's interior, it's going to be given by the system. So all that changed here relative to the equilibrium characterization is that in the denominator here, we suddenly have a sum rather than just an individual cost, because the social planner is considering everyone's costs. So when they're thinking about the cost per speed trade-off, they're thinking about the overall cost rather than an individual cost. So that hence the difference kind of on an intuitive level. Now, in terms of the stopping boundary, the social planner optimally uses a drawdown stopping boundary as well. Now, the precise formulation for the drawdown size that the social planner utilizes requires a little bit of work, but just to give you kind of a flavor of why we should expect it to look like this, notice that in the denominator, basically what we have here is just the number of people that you're going to terminate next. So these are the people who are going to be affected. And in the denominator, we have this cost per speed. When you're searching an alliance A sub k and in the consecutive alliance A sub k plus 1. So this is basically the marginal benefit from including these extra people you're going to terminate in terms of the cost per speed. So this is not a proof, not even an intuition, but hopefully it gives you some notion for why we might expect these things to show up in these terms. Okay, now some features of the solution we think are a little bit interesting. So optimal search scopes actually decrease as alliances shrink, in contrast with what happened in equilibrium. So in equilibrium, free riding implied that as alliances shrink, the search scope actually increase. So the pattern is completely the opposite. And we see greater search scopes and drawdown sizes than in equilibrium. So this is in some sense externalities. There are also deterministic exit waves, but they're possibly different than equilibrium. Now, in general, identifying the optimal exit wave path is actually a challenging problem. It's a combinatorial problem because you need to consider all ordered partitions of agents, but it's much simpler with well-ordered costs. So with well-ordered costs, we actually have a very simple algorithm for identifying the optimal exit ways, which kind of resembles greedy algorithms for those of you who are familiar. All right, so I'll just end with one example, a truly numerical example, just to give you a sense of how these things could differ. So this is a particular case of well-ordered cost where the costs are exponential and we have only 3 agents, so kind of as simple as it gets. And in this figure, we're restricting attention to the parameters such that the welfare maximizing solution is just to have everyone exit at the same time. And what you're seeing in the figure here is, recall that the person 1 here has a search scope of e to the sigma. All we need to account for are these parameters beta 2 and beta 3. And because we assume that beta 3 is greater than beta 2, that's why we're seeing the figure above the diagonal. And when beta 2 and beta 3 are very close to 1, this means that all of the agents have very similar costs. And in that case, we're in this peach color little shape that corresponds to even equilibrium leading everyone to exit in the same way. As we move on this diagonal, but increase beta 2, what we see here is that in this green thing, so here we're increasing 2 and 3, but we're keeping them very close to one another. then 2 and 3 are sufficiently close to one another that they exit together, but they're far enough from agent 1 that agent 1 exits in isolation. And similarly for this yellow figure here. And last, when all agents' costs are sufficiently far from one another, the agents exit in equilibrium independently, so not at the same time, each in its own time, in contrast to what the social planner would like. All right, so to conclude, we think this is a tractable model of collective search in a team. We have a full analytical characterization of the search scope and stopping boundaries, and they're, to us, a little bit, at least, remarkably simple, or we didn't expect them to be so simple. There's an endogenous exit wave sequence, which is deterministic in terms of order, but stochastic in terms of timing. And the equilibrium exhibits lower search scope, less search, and different exit waves than the optimum. And we hope that this kind of provides a laboratory to answer various design questions. So the optimal team composition, optimal contracting in a team, and so on and so forth. So that's all, folks.
Okay, thank you very much. Well, I have some questions, but do I have any questions in the room? Or maybe, yes, okay.
Yeah, thank you for a great talk. If I get it right, equilibrium search scopes are too narrow, right?
Always. They're too, yes, they're too low, yes.
Okay, then my question is this. Do you think it is possible, I'm not suggesting to do that in this paper, but I'm just curious. Do you think it is possible to develop an extension of your model in whatever respect, maybe working with a broader class of sample processes or just whatever, so that you can have sometimes too narrow equilibrium search scopes, sometimes too broad equilibrium search scopes, and a borderline case where you actually have optimal equilibrium search scopes? Thank you.
Yeah, I think one cheap way to do this is that I described everything through a linear process where the variance is the sum of the individual search scopes, but in general, all the analysis would translate directly if we assumed any sort of aggregation function of the individual search scopes. So if you have some forms of substitutes through the production technology, then you might get this sort of thing. But it's an interesting question. We haven't done that.
Okay, more questions? Here, let me add something. So we are living in a Markovian world, right? So everything is only state dependent. There's no time dependence. But if I know that another player is very close to dropping on tomorrow, will I reconsider my decision? So if in equilibrium, I know the sequence, right? So I have correct beliefs about it.
Yeah.
Do I ignore this information, or do I take it into account when optimizing?
So if you restrict the time, so okay, with no restriction on the stopping boundaries, you could construct weird coordination failures where just because you stop early and I believe you stop early, I stop early as well, even though both of us would want to stop later. That's why I kind of mentioned this in passing that in our proposition 2, we're assuming this for uniqueness, we need this mild weak dominance restriction. So given the search scopes, if you allow me only weakly undominated stopping boundaries, then it stops mattering. You can consider whatever you want, and this will be the unique best response. Now, with respect to non-Markovian strategies more generally, it's an interesting question, you know, for those of you who know the experimentation literature, there is some suggestion that their non-Markovian strategies kind of revive efficiency. So you might ask whether this is the case here, and the answer is no. And the reason is that I told you that the social planner wants people to search for too long. And it's very hard to penalize someone for dropping early. There's just no way to penalize them. That's kind of the intuition. So you can't actually get to efficiency with non-Markovian strategies. But hopefully, am I answering?
Yeah, I did. Yeah. So there is no folk theorem like in this setup.
No.
Oh, okay. So I guess that's it. Let's thank the speaker.
Thank you.
And